So once again, welcome to a new problem. This time we have a bone that's sitting on a surface and it uh, has a surface area or cross-sectional area given by 3.6 centimeters squared, and we always want to transform that to meters squared by multiplying um, by 1 meter squared over 100 centimeters squared. And this is going to give us 3.6 times 10 to the negative 4 meters squared. Also, the height of the bone is 22 centimeters. The original height of the bone is 22 centimeters. We want to change that to meters, so it becomes a 1 meter of 100 centimeter unit conversion, and we end up getting 0.22 meters. This is the information that were given in the problem. Also, another thing that happens is there is a force being applied on the cross-sectional area. That force F, we'll call it in newtons, 3.3 times 10 to the 4 newtons. That's the force being applied. Our goal in part A is to determine if the bone will the bone break. If the stress sigma is greater than the compressive strength of the bone, then obviously the bone is going to break. Absolutely. The compressive strength of the bone is 170 megapascals, as you can see that. And so that's the first thing we're going to find out in the problem. The second thing we're looking for in the problem is that if the bone does not break, what's the change in length that we have if the bone does not break? So in part A, we have to compute the stress, which is the force per unit area. We're given the force as 3.3 times 10 to the 4 newtons, and we divide that by 3.6 times 10 to the negative 4 meters squared. When you simplify that, we get the stress as being equivalent to 91.67 Newton per meter squared. And obviously, if you compare that to 170, it's less than that. So the stress is less than the compressive strength. So we'll say the bone does not break. Because the forces balance out. I mean, the force that's being applied is less than the compressive strength that the bone can take. So the bone itself doesn't it doesn't cave in, it doesn't break. Now, in the next page, we're gonna see by how much does the length change, given that there is a force being applied on the bone itself. Now, there's a relationship between stress and Young's modulus that's connected to the change in length and the original length. So sigma E, this is the stress, and this is the Young's modulus of elasticity. And the Young's modulus of elasticity, it's given us The value of that is 15 times 10 to the 9 Newton meter squared. This is going to help us compute delta L, which is sigma over E times L naught. And this becomes sigma is the same as 91.67 Newton meter squared. And then L naught is the same as 0.22 meters. And then Young's modulus is 15 times 10 to the 9 Newton per meter squared. And that gives us the change in length as being equivalent to 1.33 millimeters, or rather 1.3 millimeters. We can round it off if you change it to millimeters. So, hope you enjoy the problem. Feel free to send any questions or comments, and have a wonderful day. Okay, thanks. Bye.